Welcome to Algorush, where we break down the complex and sometimes mind-bending logic behind the systems that run our world. So let's just jump right in with the big question. Is it possible to have it all? Can a data system be blazing fast, super efficient, and elegantly simple all at the same time? I mean, that's the dream, right? But as you're about to find out, when you're engineering these kinds of systems, you're up against some fundamental laws. You just can't always get everything you want. And that brings us to this idea. You probably heard this in other contexts like project management. You can have it fast, cheap, or good, but you only get to pick two. Well, guess what? High-performance data systems have their very own version of that exact same impossible triangle. And here's the absolute truth at the heart of it all. Every single choice you make has a cost. When you crank the dial way up on one thing, you can be sure that the dial on something else is going to have to go down. It's this constant, delicate balancing act, a game of trade-offs where every decision means you're paying a price somewhere else. So this isn't just some vague feeling that engineers have. There's actually a formal name for this challenge, a model that describes these trade-offs perfectly. It's called the RUM Conjecture, and it's basically the rulebook for our impossible triangle. The RUM Conjecture tells us we're juggling three competing forces. You've got R for read overhead. That's how much work it takes to find the data you're looking for. You've got U for update overhead, the cost of writing new data. And finally, M for memory overhead, which is just how much space the whole thing takes up. And the conjecture is crystal clear. You can be great at two of these, but you will always take a hit on the third one. And this table just lays it all out, plain and simple. You want lightning-fast reads and updates? Fine, but get ready to pay a fortune in memory. Okay, what if you're on a budget and need fast reads and low memory usage? Well, then your updates are going to slow to a crawl. And that last one? If you optimize for quick updates and low memory, yeah, get ready for some painfully slow reads. See? There's always a tax to pay. All right, let's make this real with an example. Imagine we're building a system where speed is everything, like a social media app where millions of users are posting updates every second. The number one priority is making sure that when someone hits post, it's instantly live. We need insanely fast writes, fast updates, and we're willing to make some sacrifices to get there. So how do we get that speed? Well, the strategy is actually beautiful in its simplicity. We just use an append-only design. So instead of going back and finding old data to change it, which is slow and complicated, we just write any new piece of information to a brand new file. Think of it like adding a new page to a logbook instead of trying to erase something on an old page. It's incredibly fast and dead simple. Okay, mission accomplished, right? We have our lightning-fast updates, and since we're just creating simple files, our memory footprint is pretty low. So looking at our RUM triangle, we've optimized for U and M. But the conjecture warns us there is no free lunch. So what's the catch? Well, now we have to pay the read tax, and it's a big one. And that tax is called read amplification. Here's the problem. Because we never change old files, the complete history of a single piece of data, like, say, a user's current profile picture, could be spread out across tons of different files. To find the latest version, you literally have to go on a treasure hunt, checking file after file to piece the story together. Just picture it. You need to find one specific key. So the system has to go check file 1. Nope, not in there. Okay, let's open file 2. Still no luck. Now we have to check file 3, then file 4, and on and on. With every single file we have to check, the whole process gets slower and more frustrating. And just how many files are we talking about here? Well, the answer is N. And that N is what should scare you. Because N isn't just a handful. It could be dozens, hundreds, or in a really busy system, even thousands of files you have to check just to find one thing. This is a system that's a dream for writing data, but has become an absolute nightmare for reading it. So, are we stuck? Is this design just fundamentally broken? Do we have to just accept this terrible trade-off? Absolutely not. This is where truly clever, elegant engineering comes into play. If the problem is checking way too many files, what we really need is a shortcut, a way to know really quickly which files we can just ignore. And that shortcut is the Bloom filter. Honestly, the best way to think of a Bloom filter is like a super efficient bouncer at a club. This bouncer can't tell you for sure if your friend is inside, but they can tell you with 100% certainty if your friend is definitely not on the list. And just getting that definite no saves you a ton of time. And that's the magic of using probability here. If the Bloom filter for a file says, nope, that key is not in here, that's a guarantee. You can trust it completely and just skip that file. Boom, you just saved a bunch of work. Now, if it says, yeah, it might be in here, you still have to go look. It might be a false alarm, a false positive, but you'll avoid countless pointless searches for the ones that give you a definite no. So in practice, it's pretty slick. We just attach a tiny little Bloom filter to each of our data files. Before we do a slow, expensive search inside a file, we ask its filter first. Hey, is there any chance this key is in here? If we get that hard no, we just skip the file entirely and move on. By doing this, we can slash the number of files we actually have to read, which pretty much solves our read amplification problem. And that brings us right back to where we started, our impossible triangle. We found this incredibly clever trick to manage our slow reads, but did we actually break the rules? Did we somehow find a loophole and beat the RUM conjecture? And the answer is, nope, not at all. The Bloom filter doesn't break the rules. The RUM conjecture is still the law of the land. What it does, and this is the brilliant part, is it lets us manage the cost we chose to pay. Instead of paying that brutal tax in the form of slow read times, we're now paying a much smaller fee. It costs us a little bit of extra memory to store the filters and a tiny bit of CPU to check them. We've basically converted a crippling debt into a small, affordable payment plan. And that really is the biggest lesson here. There's no such thing as a perfect system. You can never escape the trade-offs. The true art of engineering isn't about eliminating weaknesses. It's about understanding the constraints, knowing what you have to give up, and then choosing your